we need to get started. But before I do, let me turn the microphone down because it's a little bit hot right now. Better. So today we're going to cover one of my favorite topics in Chemistry 1. But before we do that, a couple of things to wrap up from the previous chapter. All right, there is one announcement in the notes this time about a meeting for AMSA, the American Medical Student Association. Details are in there. Can we just take a moment to admire the surgeon who's looking at the camera during the middle of a surgery? I don't know if that's what they teach you in med school, but there it is. Okay, and then today the major topic is going to be on to Chapter 4, which will not be on the first exam. The first exam does start on Monday, and since it's the last class period, I will remind you that we're taking the exam in CASA. I forgot to look up which CASA location. Does anybody know? Garrison. Okay, so make sure you go to the right one. We occasionally have students going to the wrong CASA, and that obviously causes issues. So Garrison is the one over by Hoffhein's Pavilion, or the basketball practice gym is over there now. So make sure you know where that is, and then make sure you go. You bring your ID. So you'll need your Cougar card, as they call it, because everything here is Cougar something or another. And you will also make sure that if you're going to be late, make sure you're no more than 15 minutes late, or 14, I guess is the better way to put it. So if you're 15 minutes late or more, they won't let you in, and there's nothing I can do about that. So be there on time, show up with your ID so that you can get into the test and take it and not have any additional worries about it other than just what's on the test itself. Okay, so like I said, we're going to wrap up the last little thing we have here in Chapter 3. This will be on the exam, the first 2 slides, I guess, today. And we have one more class of compounds that we have to learn how to do nomenclature for. We're going to talk more about acids later on in the semester and some of the chemistry that they do, but for now we're just learning what they are and how to name them. So we have to be able to recognize what an acid is. It's a type of covalent compound, so it's typically going to be all or mostly nonmetals in the formula, but it's going to be basically an anion. So one of the nonmetal anions, either a simple monoatomic anion from the, typically the halogen series especially, or one of the polyatomic ions that we introduced last time. You have a whole table of to learn. So it has an anion in the formula, but it's going to be paired, instead of with a metal, it's going to be paired with hydrogen, which is formally going to be thought of as H+. So hydrogen with a positive charge paired with that anion in the right ratio, again, to balance the charge. So that's what the formula will look like. It will start with H, it'll start with hydrogen, and then it'll have some anion after it. All right. So there are 2 types of acids that we're going to learn how to name, and one of them are binary acids. These are in terms of their chemical formula anyway, the simpler ones. So these ones are H+ paired with a monoatomic anion. Now, in the tables that I gave you last time, which I reproduced from the book that we expect you to be familiar with for the exam, there is a list of acids, both types, I guess. You don't necessarily need to memorize the names you don't need to memorize all of that list, because there is a systematic way that we name them. So as long as you can recognize what an acid looks like and know the rules for naming them, you don't have to learn all of them by rote memorization. So again, a binary acid is H+ with a monoatomic anion. As the name binary suggests, it only has 2 elements, hydrogen and something else. And the classic examples of these are the halogen acids, so like HF, HCl, HBr, HI, and then there's a couple others from other groups, like you can form H2S. We don't really classify water, H2O, as an acid, although it does have the same type of formula. We'll get into reasons why that is later, but these are some of the more common binary acids. And the way that you name them is, it's a 2-word name. So the first part of the first word is the prefix hydro. So hydro tells you that it's a binary acid. The second part of the first word is just the root name of the anion. So as we said last time, when we're naming covalent compounds, you use that root anion name as part of the name as well. But then instead of using the IDE ending or some other ending, we change the ending to IC. So the first word has three parts to it. Hydro, which is always there. The middle part tells you what anion is part of that acid, and then you put IC on the end to indicate that it is an acid. And then the second word in the name is just acid. So that's all there is to that part of it. Okay? So it's a two-word name. So as an example, if we have HCl, we start with hydro. Cl is chlorine, so that gets the chlor root name, and then we go HIC as the ending, and then acid. So hydrochloric acid, you've probably heard of that before. That's where that systematic name comes from. So a binary acid, they're all named the same way. So hydrofluoric, hydrobromic, hydroiodic, hydrosulfuric, and so on. Okay? So if it has hydro in the name, it's going to be a binary acid. The other type of acid is called an oxoacid, and this is going to be H plus paired with a polyatomic ion. Now, if you've studied your polyatomic ions yet, you'll notice that most of them are going to be some central atom surrounded by oxygen, so they're what we call oxoanions, meaning they have one or more oxygen atoms in the formula. So most of the common anions, like the one we talked about last time a lot when we were doing Lewis structures, which is NO3 minus nitrate, that's an oxoanion, nitrogen at the center surrounded by oxygen. There's sulfate, which is sulfur with oxygen, sulfite, which is sulfur with a different number of oxygens. All those are in those tables you have to learn, and those are all called oxoanions. And if those oxoanions are paired with H+, so they're negatively charged and they have H+ balancing the charge, those would be classified as oxoacids. Now keep in mind, we'll typically give you hints about how to do this if we ask you to do it, but in these oxoacids, they are covalent compounds, so they're the hydrogen is going to be covalently bonded, and it's going to be covalently bonded to one of the oxygens as part of the anion. So the hydrogen does not get bonded to the central atom of the oxoacid, it gets bonded to one of the oxygen atoms, or if there's two hydrogens, they get bonded to two of the oxygen atoms of the anion. So that's kind of how they look structurally, but that's not terribly important for today. So a couple of examples of oxoacids would be, if you take NO3 minus, which is nitrate, it would require one hydrogen H plus to balance the charge. So HNO3 is a oxoacid. If we have SO4 2 minus sulfate, that has a 2 minus charge, so the acid of sulfate would have two hydrogens in it to balance, so it would be H2SO4. So the number of hydrogen atoms in the formula, which is again formally H plus, is how many you need to balance the negative charge of the anion. So those polyatomic anions range in charge from -1 to -3. Depending on what that charge is, that's going to determine how many hydrogens you have in the formula for that acid. So that's HNO3, H2SO4. And the way we name these is you take the root name of the anion. So again, these acids are all named on the basis of what anion they contain. So you have to, again, know nitrate, sulfate, chlorate, perchlorate, all those different things. Now, the root name of the anion, you don't just name the anion, but you put a different ending on it. So again, the endings are either IC or sometimes OUS, and I'll tell you how to decide which one of these to use in a second. So you change the ending of the anion. Most of these anions end in ITE or ATE, as we'll see, and you change that ending to either IC or OUS for the acid part, when you're naming acids. And then, again, the word acid goes on the end. All right. So the way we know which ending to use is that if you have an anion that ends in ATE, that becomes an IC ending in the acid. So this HNO3, NO3 is nitrate with ATE, so that would become nitric acid. If you instead have an anion that ends in ITE, that's when you use the OUS ending for the acid. So for an example, if you had HNO2, NO2 minus is nitrite. Typically, if you have these oxoanions, the pattern you can recognize is that they have different numbers of oxygens. The one with fewer oxygens is ite. The one with more oxygens is ate. So when you have NO2, NO3, NO2 is nitrite, NO3 is nitrate. Same for sulfite and sulfate, although it's SO3 and SO4, the different numbers of oxygens, but the same pattern. And then, so this is because this is nitrite, this would be nitrous acid. So you have that difference illustrated there. This one I'll draw down here is nitric acid. So again, the ending IC or OUS tells you whether the anion is an ate ending or an ite ending. All right, so that's how we name acids. Again, very systematic, and really in this course, there's only maybe a dozen or so common acids that you'll encounter. So if you're familiar with those, I think you guys are all smart enough to learn 12 things, and And there is a system to it anyway, so you don't have to memorize all of them, like I said. And that's all we're really going to do for acids. So just a couple examples of how to name acids. So we want to give the molecular formula for hydrofluoric acid. So when you're looking at acid names, remember the dead giveaway for whether or not it's a binary acid is the prefix hydro. So if it has the prefix hydro in it, that means it's a binary acid. So you look at that first. And because it's a binary acid, it can only have 2 elements present. So that gets rid of C and B because, again, binary acids would not have 3 elements. They would have just 2. So it can't be those 3, or those 2, sorry. And then we just have 2 choices, HF or FH. I guess technically they're the same thing, but remember by convention we put H first in the formula. So the best answer in this case is going to be choice A, HF. That's hydrofluoric acid. We put hydrogen first, then the anion when we're writing the formulas for acids. All right, so again, a lot of these are going to be multiple choice type questions on the test. It's hard to do much else in Blackboard for many cases. And if you see hydro in the name of the acid or hydro in the answer choice, you should know that that goes with a binary acid. All right, and then the next one here is a little bit more perhaps challenging. We have H2CrO4, and we want to give the proper name for that. This is the rare case of an acid that includes a metal, chromium, in the center, and that's because there are a couple of polyatomic anions that have metals at the center. So there's permanganate, MnO4-, and then there's this one, CrO4. Now the formula tells us that the charge on the anion is going to be what? Even if you don't remember, it's going to be 2- because there's 2 hydrogens in the formula, but we should remember that there's 2- charge anyway, because this is one of our polyatomic anions that we need to know. This, as you'll recall, is called, or hopefully recall by next week, is called chromate. All right, so that's the name of the anion. And then remember, when we have a polyatomic anion, the way that we name the acid that's associated with that is we change the ATE ending to an IC. So that's going to be chromic. And then we lop on the term acid at the end. So this would be chromic acid. So the correct one is C. As far as I know, there is no perchromate anion, so that's not going to be one that we'll ever see. There's also, to my knowledge, not a chromite. That would give you chromous acid. And again, you don't use hydro as a prefix when you're talking about non-binary or what we call oxoacids. So the only choice that works is choice C. And again, it's about knowing the names of the anions on that table and then translating that into an acid by changing the ending. So any questions on acid nomenclature? So that's all we're going to do with it for now. You'll see it again reviewed on the homework assignments and things this week. All right, so this is going to be, I'll put a big star here. This is end of exam 1 material, in case you're concerned about that, which you likely are. So that's the last thing. Again, my notes, I've gotten questions about this. I do attempt to be comprehensive, where if you study the notes, you should be okay for the test. But again, there could be little things here and there that you want to pick up from the textbook, and you'll figure those out by doing homework assignments as well. But we're now going to move on to Chapter 4, which will not be on the first exam. Will be on exam 2. But it follows very closely from some of the things we did in Chapter 3. So in Chapter 3, one of the big topics that we finished up last time was drawing Lewis structures. And we said that Lewis structures are 2-dimensional representations of molecules. We just kind of randomly arrange the atoms on the paper and draw the bonding and non-bonding electrons. What we're going to start with in Chapter 4 is how to predict the 3-dimensional shape of a molecule. And your first thought might be, why do we care about the 3-dimensional shape of a molecule? There are reasons. So as we'll see as we go through this chapter, the shape of a molecule is related to some of its key properties, especially things like polarity, as we'll talk about a little bit in this chapter. And then the 3-dimensional shape of a molecule also is related to the bonding that's involved. How are those atoms actually bonding to each other? What orbitals are involved? How, all that kind of good stuff. So we have to start with the shape, and getting the shape, as we'll see, requires a good Lewis structure. So if you can't draw Lewis structures, then you're not going to be able to do this part of the course either. So this topic of Lewis structures is going to come up a lot in Chapter 4 for a lot of things we do. You need a Lewis structure at the start, and that allows you to then make some predictions about the shape or the bonding or something else. So the method we're going to use to predict 3-dimensional shapes is called Vsepr. It's an acronym, as you might suggest. Some people pronounce it Vsepr. That always bothers me because that's not how it's spelled. But if you pronounce it Vsepr, I won't be too angry at you. So anyway, What it stands for is valence shell. So it deals again with valence electrons primarily, or exclusively, I guess is a better way to say that. And then it's electron pair repulsion. So Vsepr. And the whole idea of this approach is that we have some central atom that has a bunch of electrons surrounding it, either bonded to other atoms or lone pair electrons, as we saw in the Lewis structures that we did, or some combination of those two more often. And what we're going to do is we're going to take those electrons on the central atom, those valence electrons, and we're going to place them around the central atoms and try to get them as far away from each other as possible. All right, because remember, electrons repel each other, so you don't want to force those electrons that are surrounding the central atom into any closer to each other than they have to be. So you want to get them as far away from each other as possible. And so really the essence of this approach is not so much chemistry. I mean, you have to know some chemistry to do this, obviously, but this is really a geometric approach. So we have a certain number of things that we're putting around a central atom, and we want to know what shape do those things have to occupy to be as far away from each other as possible. So if you have a background in geometry, it helps for this, although it's not required. And as we'll see, these shapes are basically predicted by, how many things do we have in the central atom, and how do we get those things arranged and spread out as far as possible from each other. So there are a couple of other definitions that go along with this then. And so when we ask you to predict the three-dimensional shape of a molecule, there are two things we might ask you about. So one is called the electron group arrangement. So this is going to be the three-dimensional geometric shape, and as we'll see, there's really only about 5 of them you have to know for this, for the electron group arrangement. And this accounts for both the bonding and the non-bonding electrons. So as we said, in many cases, the central atom is going to have some combination of bonding electrons surrounding it that are shared with other atoms in the structure, or they might have some non-bonding electrons, those lone pair electrons that often end up on the central atom. And the electron group arrangement is just the shape occupied by all of those things together, all of the groups that surround the central atom. The molecular shape is related to this, but in the molecular shape, we only consider the atoms themselves that are part of the molecule. So most techniques we use for visualizing the structure of molecules, we can't see electrons. So what we're really mostly concerned with in many cases is just the shape that the atoms occupy, ignoring the lone pairs, which are there, which influence the shape, but we don't actually directly see or visualize. So the molecular shape is the 3D shape that only the atoms themselves occupy, not the lone pair electrons. So the atoms that are bonded to each other occupy some shape. As we'll see, the lone pair electrons influence the shape, but the molecular shape basically ignores them when we're defining that. So it's kind of, you can think of this as what the molecule looks like. So we put all of the atoms in the right position, and we say, what does that shape look like? That's the molecular shape that just considers the atoms that are bonded to each other and not the locations of any lone pairs. Okay? So those are the two things we'll ask you when you're, we're going to learn how to do this today, of course. We'll give you a problem on the homework assignment, and we'll ask you, what is the electron group arrangement? What is the molecular shape? Or, both of those in some cases for this particular compound. Some other definitions before we get into the approach. Now, I think this is a little bit different than how your book does it, but I do like this sort of system of categorizing things, and I think it helps you organize your thoughts and classify things a little bit more generally. So we have what's often referred to as the AXE notation. Okay? So what do all these terms mean in this abbreviation? AX with a little subscript M, E with the subscript N. So A is the central atom. So we're going to primarily be, or almost exclusively, predicting shapes for molecules that have a central atom and then a bunch of atoms around them. So A is your central atom. And then the X and the E tells you what is attached to that central atom. What is it surrounded by? So X is an atom that's bonded to the central atom. And then E is a lone pair. Now remember that the P in Vsepr means pair, so we're always talking about pairs of electrons here. So we're going to treat all electrons in groups of 2 for this approach. So you have bonded pairs and lone pairs. And then these little subscripts M and N in this generic formula are going to tell us how many of each of those we have. So how many atoms are bonded to the central atom, or how many lone pairs does it have? And we're going to categorize them based on that combination of M and N. And then X and E, these bonded atoms and these lone pairs, these are what are referred to as electron groups. So when we say the electron group arrangement, it's going to be, again, the arrangement of all of these things around the central atom, both the bonded atoms that are bonded to it and any lone pairs that are on the central atom. So that's what we kind of generically refer to X and E as our electron groups. Now some other terminology. This is one that I definitely know that your book doesn't use, but this is how I learned it when I was your age a long time ago, and that is steric number. So steric number is the sum of M plus N. In other words, it's the total number of electron groups around the central atom. And as we'll see, this total number of electron groups dictates the electron group arrangement. That's all you need to know to figure out which electron group arrangement these things fall into. All right. So that's what we call the steric number, and knowing that number, as we'll see both in this first part of the course, allows us to predict the electron group arrangement, and then in the second part of this chapter, we'll see allows us to predict some things about the bonding of the central atom as well. So that's an important parameter for a couple of things we'll do in this chapter. And a note as we get started, so we don't cause any confusion on this, when we're counting electron groups, and especially X, these bonded atoms, the bond order between A and X does not matter. So whether A and X are attached by a single bond, a double bond, or a triple bond, we count X as one electron group. Doesn't matter how many shared electron pairs there are. The reason for that, if you're curious, let me finish writing my sentence and then go to the next one. So the bond order between A and X does not matter. X will always count as one electron group no matter what that bond order is. Now there could be more than one X bonded to the central atom, of course, but each individual atom that's bonded counts as one no matter whether it's a single, double, or triple bond. The reason is that, remember that this approach kind of wants to arrange things in space and get them as far away from each other, and whether there's a single bond, double bond, or triple bond, that X electron group doesn't really take up much different amounts of space. We'll see that there's some subtle effects of the bond order on the geometry, but in terms of classifying it into one of the major electron groups, single, double, triple bond doesn't affect things. And so we count it as one electron group regardless of the bond order between A and X. And then another parameter that we're going to often talk about in the context of molecular shape and electron group arrangement is bond angle. So bond angle is the angle between two atoms that are bonded to the central atom. With the central atom as the vertex. All right, so for example, if we have the molecule water, H2O, as we'll learn today, we would predict that water has a bent arrangement. So the HO and H are not going to be linear with each other. They're going to be bent at some angle. And the angle would be defined as this angle here. And we'll learn how to predict approximately what that is also. So we abbreviate this sometimes as with the angle sign and then the three atoms that are involved, which would be HOH, AO at the center. So it's an angle defined between two atoms that are bonded to the central atom with the central atom as the vertex of that angle. And we're going to talk about that a lot as well. So the way that we're going to approach this today is we're going to go through one by one all of the possible electron group arrangements. And I have a link here that I encourage you to check out, which I'm going to use today, that allows you to visualize these shapes. Because now we're starting to really think in 3 dimensions, and having sort of that spatial reasoning is helpful. So these models that I'm going to show you in class today and that I welcome you to play around with on your own give a nice interactive 3-dimensional model of all of these shapes. I also have some molecular model, or at least one molecular model kit in my office. I learned in kindergarten how to share my toys, so you're welcome to come and check those out. And so on. So again, being able to visualize these things in 3 dimensions is going to be helpful for you as we go through. All right, so let's start with 2 electron groups, the simplest one we're going to deal with. So here's the simulator. Again, the address is in the website. So what we're going to do is, if we're using this, and I got to try to get this out of the way a little bit more than it currently is, put it over here for now. What we're going to do with this is we have our central atom here in purple, and then each of these we can put on either bonded or non-bonding electrons onto the central atom. So if we're starting with 2 electron groups, let's put on 2 bonded atoms and see how they arrange themselves. All right, now as you can see, they go linear. They do bend temporarily when you rotate them. That's a weird bug of this program. But you can see clearly when we have 2 electron groups, we want to put them as far away from each other as possible. We put them at a 180-degree angle on opposite sides of the central atom. So when we have, no, wrong document. When we have 2 electron groups, this is going to be in my way all day today. When we have 2 electron groups, the electron group arrangement is going to be linear. All right, so we call that linear when the 3 things are all arranged in a 180-degree angle or in a line from each other. So anytime you have 2 electron groups on the central atom, the electron group arrangement will be linear. And we have 2 possibilities then when there's 2 electron groups. One of them is AX2, meaning that both things that are bonded to the central atom are other atoms, and there's no lone pairs. So in that case, that's exactly what I showed in the simulator, is an AX2 molecule. Central atom, 2 atoms bonded to it. Okay, so that's what we call AX2. And when we draw that shape on paper, again, it's pretty simple to draw. It's just a linear arrangement of those 3 atoms. As we will see when we go through this, there are a lot of different AXE notations and a lot of different molecules in the real world that have a central atom with 2 other atoms bonded to it, and there's only 2 possibilities for that. You'll either have linear or bent. So in this case, the 2 want to get as far away from each other, so they are a linear arrangement. And the bond angle is exactly 180 degrees. Okay? Now, one thing we'll also see as we go through this is that you have your electron group arrangement, which again is dictated by the total number of electron groups. And then when you have the types of molecules that don't have any lone pairs on the central atom, that are just AXN, AX2, AX3, AX4, whatever, with no lone pairs, the electron group arrangement and the geometry are going to be identical. So 2 electron groups will always have a linear electron group arrangement, and then when it's AX2, the molecular geometry is also linear. So sometimes those 2 are the same as each other, as we'll see. It'll become more obvious as we do the more complicated ones. Now we also have AXE, so that's another 2 electron group arrangement that would have, again, 12, 2, 1X, and 1E in this case. So if we go to the simulator website, we're going to take one of these off and put a lone pair on. This one I think is pretty trivial because you only have 2 atoms bonded to each other. Okay, and then lone pair on the other side. Remember, the 2 electron groups still go linear with respect to each other, so the atom is pointing in one direction, the lone pair is pointing in the other direction. And then when we classify that geometry, or draw it out, it's just going to be AX, and then a lone pair on the other side, which is sometimes drawn as this, or just put directly on the central atom A. This would also be called linear. This is trivial. If you have 2 atoms bonded to each other, they can't be anything but linear. I dare you to try to draw a shape with 2 vertexes that's anything but linear. Try it. It won't work. And the bond angle we don't have, because remember, a bond angle requires 3 atoms, 2 bonded to the central atom. So this doesn't even have a bond angle associated with it because there's only 2 atoms total. And essentially, without thinking about it, all diatomic molecules are going to be linear. So if we're nice enough on a homework assignment or a test to say what is the molecular geometry of something with only 2 atoms in it, whether it be 2 different atoms or 2 of the same atoms, they have to be linear. You don't have to draw it out or think about it any more than that. Okay? Now, if it's 3 or more atoms, the story is obviously more complicated. But if it's only 2 atoms, whether it's something like CO, carbon monoxide, 2 of the different atoms, or Cl2, chlorine, which has two of the same atom. Those will always be linear if there's just two things bonded to each other. Now let's get on to the more interesting ones. So let's do 3 electron groups now. And there's going to be 2 possibilities for that would have 3 electron groups. All right, so one of them is AX3. Now let's first figure out how these electron groups arrange themselves. So let's put 3 electron groups around the central atom. Using your geometric intuition, what do you think is going to be the way that these electron groups are going to arrange themselves to be as far away from each other as possible? A triangle, right. So if we put 2 more on there, we will see that they end up in a triangle. Okay? So that's what 3 electron groups looks like to get each other as far away as possible. If we look at the side view of this, we will see that it's a little bit hard to rotate on using a touch screen, but we can kind of do it. If we look at a side view, we see that it's totally flat. So it's a totally flat triangle to get those 3 things as far away from each other as possible. So the electron group arrangement, let me abbreviate. I'm going to write that a million times today. So let me just call it E group arrangement, abbreviate it, is going to be what's called trigonal planar. All right, so chemists are a little bit pompous. We don't just say triangle, we say trigonal planar. But it means the same thing. It's just a triangular shape with 3 things all equidistant from each other in the same plane. So if we have an AX3 then notation where all 3 of the electron groups are just atoms bonded to the central atom, that would look like this. We can still draw it flat, so it's pretty easy to draw. And again, in this situation where all of the electron groups are bonded atoms, the electron group arrangement and the molecular geometry have the same name, trigonal planar. All right, that's going to always be true whenever you have no lone pairs in the central atom. That electron group arrangement also describes the molecular geometry. And the bond angles in this case, if you remember from high school geometry class, are going to be 120 degrees. Okay, because if we go around, there's going to be 3 bond angles in this molecule, this x to that x to that x, that x back to the first one. That whole thing is 360, so each one is 120. Okay, so 120 degree bond angles when you have 3 electron groups. All right, and then the other possibility with 3 electron groups is AX2E, so we're going to remove one of the bonded atoms and replace it with a lone pair. So we take one off and put a lone pair on. And as I said before, when you have 3 atoms bonded together, there's only 2 possibilities, linear and bent, and I think we can pretty clearly tell that this one is bent. You will sometimes see them referred to as V-shaped also. That's not hard to imagine also. This again is still, well, you only have 3 atoms, so they have to be in the same plane. Again, geometry doesn't let you do anything otherwise, but the arrangement of those would be bent. Again, there is the lone pair occupying the 3rd position. It's there. It influences the geometry. That's why they're bent and not linear in this case. But we call the molecular geometry just bent because that's the shape that the 3 atoms themselves make up. All right, so when you have an AX2E, you would have the 3 electron groups are still going to go trigonal planar. So you always start with that same basic arrangement. One of those is a lone pair. The other 2 are bonded atoms X. And this is what we call bent or sometimes V-shaped geometry. I think bent is the more common one. Now in talking about the bond angles for this one, we are still using a trigonal planar electron group arrangement. So the bond angle, there's only one in this case between these 2 X's. It's going to still be close to 120 degrees, but it's not going to be exactly 120 degrees anymore. So we'll talk about this in more detail later on. But basically when you have lone pairs repel more strongly than bonding pairs. They take up more space if you want to think about it that way. And so these are going to push down a little bit on these bonding pairs, and it's going to make the bond angle a little bit less than 120 degrees. It's impossible to predict exactly what that's going to be. It depends on what the identity of A and X are. But you know it's going to not be exactly 120 degrees when you have a lone pair involved. So lone pairs do compress the bond angles a little bit, but without any other information, you would still predict that they're 120 degrees or at least close to that. Okay? So that's bent or V-shaped. We're going to move on now to 4 electron groups. So we're going to go all the way up to 6. We have a few more to do. So with 4 electron groups, let's see what we do. And this is the first time we have to think about things 3-dimensionally, so it's a little bit more difficult in this case. So we're going to put a total of 4 on there. All right, and you can kind of see what this looks like as I rotate it around. One way to think about this shape, I'll tell you what it's called in a second, but one way to think about it is that it's 2 V-shaped things that are sort of interlocked at a 90-degree angle. So you have two triangle planes, and then you have two of those that are locked in a 90-degree angle relative to each other. So this one's harder to visualize, as I said. So these simulators or the molecular model kits that I have in my office, or maybe some of you have yourselves, if you are as enthusiastic about chemistry as I am, those will be helpful for visualizing this. Now, what do we call this? We call this electron group arrangement. We call that tetrahedral. The name is not intuitive. It comes from the shape that if you draw sides through all the vertexes, if you connect all the vertexes on the outside, you get 4 triangles, and that's why it's called tetrahedral. But that molecular shape. Now, how do we draw that? The way we draw it is it's now 3-dimensional, so we can't just use flat pictures anymore, unfortunately. As I said, 2 of the atoms we're going to have just at a bent angle. And then we have 2 others that are in a plane perpendicular to this. And the way we indicate that is with little dashes and wedges. So when you draw a solid dash like that, sometimes colored in, and put an X next to it, that means that this X atom is not in the plane of the page, but is coming out towards you. Okay? And then if we draw one like this that has a dashed wedge, that means that X is going back into the page away from you. So when you're trying to indicate 3-dimensional pictures, which is hard to do on paper or on a tablet, you use dashes and wedges to indicate vectors that are coming out towards you or going in the page away from you. And again, we call this tetrahedral. We'll go back to the rotating model in a second, which might be a little bit easier to deal with. So it's tetrahedral. The bond angles in this are not nearly as easy to rationalize as some of the others, unless you're really good at 3-dimensional geometry. And they come out to this magic number that you'll have to remember, which is 109.5 degrees. Okay? So that's the bond angles between A and all the X. So all of these positions are equivalent. All of the X's are equidistant apart from the other ones in the structure. Okay? And again, going back to that now, if we rotate this around, we can kind of see it. The orientation I drew it in is approximately like this. Let's see if I can get it just how I drew it on the page. It's something like this. So again, you have the 2 that are all in the same plane with the central atom. Then you have one that comes out towards you, which we on paper draw as a solid dash, and then one that goes away from you that we would draw as a dashed bond to indicate that it's going away. So that's how I draw it on paper. This is, again, a more accurate 3-dimensional representation. Now, within the 4 electron group possibilities, we have also AX3E, so we can replace one of these with a lone pair. And this geometry, I think, is a little bit easier to see. It looks like basically a 3-legged stool. So again, this is the top, and then you have the 3 legs coming down, all at angles from each other. So that's what AX3E looks like: 3 bonded atoms in 1 lone pair. And then we draw that like this. Again, it's still a tetrahedral electron group arrangement, so we still draw the same arrangement of all the electron groups. Now one of them is a lone pair. All of the positions are equivalent, so where we put the lone pair doesn't matter. The easiest way to see this shape, I think, is to put it on top like this. And then again, you have sort of the 3 legs of the stool coming down. And what we call this is trigonal pyramidal. So it looks like a pyramid with a triangular base, so the name is trigonal pyramidal. And again, the bond angles in this one, because it's a tetrahedral electron group arrangement, we would expect them to be very close to 109.5, but the lone pair compresses them to some extent. So these are going to be a little bit less than 109.5. The exact amount less, again, depends on what the molecule is. You can't predict that. There's no way to predict that. But it's going to be, again, the same basic arrangement of electron groups, but one of those is now a lone pair. All right, so that's AX3E. And then the last one that we have for 4 electron groups is AX2E2. So 4 total electron groups, and then one of them is going to be, 2 of them are going to be atoms, 2 of them are going to be lone pairs. So we take off one of these and put one more lone pair on. And this is AX2E2. We're back to a situation where we only have 3 atoms. So as we said, the only choices are linear and bent, and that very clearly is another one that gives you a bent geometry. Okay? So AX2E2 is another example of bent or V-shaped, but usually bent is the terminology we'll use. And there are still 2 lone pairs that go into the opposite plane, as we'll see. as we rotate this around. So there's the two lone pairs there still, but the geometry that the three atoms themselves occupy is again V-shaped or bent. Okay, so the way we draw this, if we were drawing it in the typical orientation that I've been using, we draw it like that. We put lone pairs on two of the positions, and you put the X's in the other two. Again, which two get lone pairs, which two get atoms doesn't matter because they're all equivalent. The more conventional way of drawing this is sort of in this orientation. And then in this way, you would have sort of lone pairs coming out and going in kind of like that. So sometimes we draw them as little orbitals, as we'll talk about later in the chapter. So there's a couple ways of drawing this, but again, it's pretty clearly a bent geometry. Or V-shaped, as I said, is the way we sometimes name that. The bond angle in this one, again, comes from the electron group arrangement being tetrahedral, which the ideal angle is 109.5. The lone pairs will compress that. They'll compress it even more now because there's two of them, so it'll be something less than 109.5 degrees. So we see now already that there are two bent geometries, AX2E, AX2E2, both give you bent geometries. The only difference would be the bond angles. In AX2E, they're going to be closer to 120 because it's derived from the triangular or trigonal planar geometry. AX2E2, the bond angles will be closer to 109.5, even smaller than what you get in the other one, because they're derived from the tetrahedral geometry. So some slight differences, but still broadly classified as a bent geometry. All right, that takes us to 4, and then the next one I think is the most complicated perhaps, which is 5 electron groups. So let's see what that looks like. And the reason this is more complicated is because this is the only electron group arrangement we'll see where there's two different positions that are not equivalent. So you have, in the 3 we've talked about so far, and then the one more we'll talk about, all of the positions where you put electron groups are all equivalent to each other, meaning they're all the same distance from the other electron groups. They all have the same angles associated with them and so on. 5 electron groups, though, as we'll see, there's 2 inequivalent positions. All right, so we're going to put 5 electron groups on, so let's put 3 more. Now let's see what this looks like. We have to get this into a good orientation. It's a little bit hard to rotate this because these molecules like to fold up when you rotate, but here we go. Okay, yeah, that's how I'll draw it. So that's what 5 electron groups looks like. Now, what exactly is this geometry? So this is what it looks like in 3 dimensions. If we turn it over on its side, and again, carefully without folding it up all together, what we'll see is that it's 3 atoms in a triangle, and then you have basically 2 sticking out above and below that triangle as flagpoles, if you want to think about it that way. So a triangle of 3, one going out of the triangle from the center, one going the other direction from the center of the triangle. So that's what the shape looks like. And so that electron group arrangement is called trigonal bipyramidal. So it's a trigonal base, triangular base, and then it's bipyramidal because you have a capping atom going above and below that triangular base. Okay, so trigonal bipyramidal. And so if we have AX5 with 5 electron groups, all of them being bonded atoms, that geometry would also be trigonal bipyramidal. So the way we draw this again requires us to use those dashes and wedges because it is 3-dimensional. So actually I'm going to draw this 2 ways, so let me move this over a little bit. All right, so one way to draw is again using the dashes and wedges. We have these 2 coming out and into the plane, and then X's in all those positions. So if it's AX5, the molecular geometry is also called trigonal bipyramidal. Anytime you don't have lone pairs in the central atom, the electron group arrangement and the molecular geometry are the same. Another way to draw this that's perhaps a little bit more convenient is remember that these 3 atoms here make up a triangle. So sometimes the way you'll see this drawn is you'll put A at the center of a triangle, and then you'll put one above and one below the triangle, X's at all those positions. So this is an equivalent way of drawing that geometry that's maybe a little bit more intuitive, showing you that there's a triangle of 3 atoms all in the same plane, and then one that goes above and one that goes below that plane. All right, so this is called trigonal bipyramidal. Now let's talk about the bond angles for this one. And as I said, this is the one geometry we have, the one electron group arrangement we have, where the positions are not all equivalent to each other. So what we'll see if we look at these bond angles, let me erase these dashed lines because they're going to get in the way of my bond angles here. Not the bond though. All right, so what we'll see is these ones I think are pretty straightforward, but there's two of them. So in the triangle, we talked about if you have a triangle of 3 atoms, what's that bond angle going to be? We talked about it a little bit earlier, 120 degrees. So remember, 3 atoms in a triangle, all are 120 degrees apart from each other. So we have this is 120 degrees. But then we also have the bond angles between what we call the apical atom, the one that sticks up out of the triangle, and the atoms that are in that plane of the triangle. And that, as we can probably tell, remember that this vector is perpendicular to the triangle, so what does that mean the angle is? 90. Okay, so this is a 90-degree angle. So we have two unique bond angles in the trigonal bipyramidal electron group arrangement. We have 90-degree angles, which are between the apical atoms and all the atoms in the plane, and we also have 120-degree angles. I guess technically speaking, we also have 180 degrees, although we usually only talk about bond angles that are between atoms that are adjacent to each other, so we wouldn't skip over. But these two are 180 degrees apart, if you want to think about that also. But we have two different bond angles, 90 and 120. And so then what this means, when we start putting lone pairs on here, is we have two choices for where does that first lone pair go. So if we're going to go to AX4E, we're going to take these 5 electron groups, and we're going to make one of them into a lone pair. And there's two possibilities for where that lone pair goes. It either goes on the triangle here, or it goes in one of these top and bottom positions. Now, what we want to do with lone pairs, we talked a little bit already about how lone pairs are more strongly repelling than bonding pairs. So if you have a lone pair involved, you wanted to get it as far away from everything else as possible, and here we have a choice for where that is. Now, it might not be obvious which one it is. Let's see what the software tells us. So if we take off one of these and put a lone pair in instead, what we can tell if we put it back in the right orientation is that the lone pair went onto the triangle. Okay? So one of those triangular positions in the molecule, as we can see better maybe in this orientation, one of those triangular positions is now occupied by a lone pair. So again, it's not maybe entirely intuitive, but we have this trigonal bipyramidal arrangement. And the place where we can put the lone pair that puts it furthest away from everything is on the triangle. So it's a little bit better to be here and have these 120-degree angles relative to the nearest neighbor atoms versus to be up here where it has 3 90-degree angles. Again, that's maybe not an obvious consideration, but that's really what it works out to be. And so the rest of these would be X's in this geometry. Now, this geometry is not very obvious, the name of it, and especially not in this orientation. So if we go back to the three-dimensional model, the way that we sort of classify this geometry is to put it on its side like this. All right, so like that. And then what you can see is if I do this carefully, we can rock this back and forth. And some of you may have played on one of these when you were a kid. See, it just folded on itself, so now it didn't do that. But anyway, what that hopefully reminds you of is a seesaw. So the geometry is called seesaw, and again, putting it on its side makes it a little bit easier to see that. So if we draw it in a side view like this, that's called seesaw. All right, someone's feeling a little bit whimsical when they named this one. But that's what it is, seesaw. And I don't know why this is. I mean, I guess it is one of the harder ones to visualize, I'll give you that. This seems to be the geometry that the most people mess up on homework assignments and tests. So prove me wrong. Don't mess it up this time. But that seems to be historically, in the few times that I've taught this course, the one that gives people the most trouble. So AX4E is going to be a seesaw geometry. And again, we still have two different bond angles here. So the ones that are still left on the plane of the triangle are going to be close to, but a little bit less than 120 degrees because of this repulsion from the lone pair, but still close to 120 degrees. And then we have this 90-degree bond angle here, which again is going to be compressed a little bit because of repulsion from the lone pair. So our bond angles are still close to 120 and 90, but they get compressed because of the repulsion from the lone pair, as they always do. All right, so that's what we have for a seesaw geometry. AX4E, question? Yep. Well, classifying something as a top view and a side view, I suppose, is arbitrary. So I just drew it like this so you can hopefully more easily see that it's a seesaw, because in this orientation it doesn't look anything like a seesaw. I've never been in a seesaw that's arranged vertically. That would be pretty dangerous, I think. So if you imagine that these are the two seats of the seesaw and this is sort of the fulcrum by which it pivots, then that's sort of the best way to draw it, to see that. It doesn't really matter how you draw it, and obviously in Blackboard we can't ask you to draw anything, but you do have to be able to identify what it looks like. And the main thing is, the shapes are helpful, I think, for visualizing, but as long as you can match up the correct Lewis structure and the correct AXE notation to that shape, you'll be good to go. What I call top and side view is a little bit arbitrary, as we said. All right, with the 5 electron groups, there's actually 2 other possibilities. So the other complication about 5 electron groups is that we have 4 unique molecular geometries. So now we're not just talking about a couple, we're talking about 4. So the other one will be AX3E2. We take one more atom off and replace it with a lone pair. All right. Now the way that this works with 5 electron groups is we saw that the first electron pair, the first lone pair, goes onto the triangle. All subsequent ones will then go onto the triangle also to stay as far away from that one as possible. So your first lone pair goes onto that triangular plane in the molecule. The second and third lone pairs, we'll see, also go onto the triangular plane to stay as far away from the first one as they possibly can. So we'll see if the software predicts that correctly. So we take off one atom and put another lone pair. And so now, as we can see, if I get it in the right orientation for you, both of those lone pairs go onto the triangular plane. And if we rotate it this way, you can see clearly that 2 of the positions of the triangle now have lone pairs on them. So within 5 electron groups, whenever you have lone pairs, they always go onto the triangular middle portion of that molecule. Okay? So we start with the 5 electron groups in a trigonal bipyramidal arrangement. It's always going to be that same electron group arrangement. But then we have 2 on the triangle. Doesn't matter which 2 positions, but if we draw it this way, it's, I think, the easiest to see what this geometry is called. Now, I guess this is also a little bit sideways, but a little bit easier to visualize. We call this T-shaped. So if you turn this one onto its side, you would also have pretty easy to tell that it's a T-shaped geometry. All right? I guess if I had to pick a favorite geometry, it'd be this one because my first and last name both begin with T. But that's what it is, T-shaped. You can clearly see it in that orientation that the molecules form a T. All right. Now, one thing that this software does not do is it doesn't really accurately show the bond angle. It doesn't show the bond angle compression. It shows them as exactly 90 degrees. But again, because there are lone pairs, even though these are ideally 90 degrees, they're going to be a little bit less than that because of repulsion. Now, I guess if you're wondering, I think this same website also has some real molecules in it where it'll show you the actual bond angles and things, so you can apply it to some real examples. It's usually, the amount that the bond angles compress when you have lone pairs is a few degrees. So, like water, which has 2 lone pairs, I think goes down to about 105 degrees instead of 109. So it's not a huge compression, but it is measurable. Same here. You wouldn't expect it to be much smaller than 90, but a little bit smaller because these 2 lone pairs are pushing back on the atoms closest to it. So that's T-shaped AX3E2. The last one we have for 5 electron groups, not the most common electron group arrangement, or not the most common combination of AXE, is AX2E3. So we're going to replace one more of those positions with a lone pair. Again, the lone pairs want to go as far away from each other as possible, so they all go onto the triangle. So if we take one more atom off and put one more lone pair to make it AX3E2, all 3 of those go onto the triangle now. And what we can see is that we're back to a linear arrangement. So still 3 atoms, 2 possibilities is going to be linear or bent. And this is the other one that gives us a linear arrangement because the 3 lone pairs all go into the trigonal plane, leaving the apical positions occupied by the 2 bonded atoms, making them linear, 180 degrees from each other. So AX2E3 is another example of linear. So we start with the trigonal bipyramidal electron group arrangement. We put lone pairs on all 3 of these positions. And then we put the X's up and below, 180 degrees apart. And the bond angle will be exactly 180 degrees. There's no compression here because the lone pairs push equally in the 2 directions. All right, so these lone pairs are pushing up on this bonded pair, but they're also pushing down on that bonded pair by the same amount. in all directions, so they stay 180 degrees apart. All right, so there's no compression of the bond angle here because they're influenced equally in both directions. All right, so that's another linear geometry, AX2E3. All right, last one before I pause for questions is going to be 6 electron groups. So this is as high as we'll go for main group compounds. So again, we're going to be doing these for the same types of molecules you draw Lewis structures for, mainly p block elements, covalent compounds, all that stuff. There are examples of metal compounds that have more than 6 electron groups, but we're not going to get into that in this course. So 6 electron groups is as high as we'll go. And again, not the most intuitive geometry, but pretty easy to understand. If we want to put 6 things as far away from each other as possible, as we'll see, it turns out the best way to do that is to put them all mutually 90 degrees apart. So if we put 6 total electron groups, so 3, 4, 5, 6, I think this is as high as this lets you go also. Yeah, so this doesn't let you have fun and go beyond 6. You have to stop there for this as well. And this is the geometry. All 6 of them are mutually perpendicular to the other one, mutually 90 degrees apart from the nearest neighbors. Now, what does that look like in space? So this is the 3-dimensional form. What this actually is, if we turn it on its side, is in some sense similar to trigonal bipyramidal, but now it has a square base. So it's a square with one atom coming out of the plane and one atom going into the plane. So a square bipyramidal would be one way to name that. Now, square bipyramid is not what we call it. What we call it instead is octahedral. And again, that name's a little bit confusing because octa makes us think of 8, but this is for 6 electron groups. It's called octahedral again because if we draw segments through all of the vertexes, you get 8 triangles as you go around the top and bottom of the octahedron. So it's 8 total faces if you draw the outer surface. So the way we can draw this on paper then is again using dashes and wedges. Would be you have a square plane that's sort of perpendicular to the page, so you're going to have 2 coming out and 2 going in, and then perpendicular to that plane you have atoms coming out and in like that. So all of these positions are equivalent again. They're all 90 degrees apart from each other, and this is how we can draw it. Or again, perhaps a better way to draw it that's simpler is you draw A at the center of a square, and you have one coming out of the square, one going into the square, X's at the corners, and those vertexes that we drew. All right, so those are 2 ways of drawing the same thing. And what we call this, again, if it's AX6, no lone pairs, the molecular geometry is the same as the electron group arrangement, octahedral. And all of the bond angles in this are exactly 90 degrees. Okay? So with 6 electron groups, we also have a couple possibilities that involve lone pairs on the central atom. So AX6 is shown here. If we replace one of those with a lone pair and have an AX5E, then we have to see what happens there. All of those positions are equivalent, so it's not going to matter where we put the lone pair. So if we take one of these off and replace it with a lone pair, we'll see that the electron groups still make an octahedron, but one of those positions is a lone pair. If we draw it in this orientation, it's, I think, easiest to see that what we have is still a square base with now only one coming out, so we just call that a square pyramid, all right, or square pyramidal. All right, so again, from the side, square base, and then one coming out of that square makes it a square pyramid. Okay? So we draw the octahedral electron group arrangement. And again, it doesn't matter where the lone pair goes, but the easiest way to visualize the geometry is to put it at the bottom here, put X's everywhere else. And that gives us a square-based pyramid. All right? And because of that one lone pair on the bottom, the bond angles compress a little bit. It's not perfectly planar anymore at the base. So basically this almost umbrellas a little bit where these X's are going to sort of pooch out of the plane a little bit and kind of compress those angles from 90 a little bit, but it's still close to 90. All right, so that's the square pyramidal geometry. And then the last one, the very last one we're going to do, which also has 6 electron groups, is we put 2 lone pairs in there. Now again, the lone pairs want to be as far away from each other as possible. So if we have these 6 positions that are all equivalent, but we want the lone pairs and we have to be as far away, where would we put 2 lone pairs? Opposite sides, exactly. So we want the lone pairs to be as far away, so those go opposite each other, and then that leaves X's in the square plane. All right, so let's see if the simulator shows that more clearly. Take one off, put another lone pair on, and you can see that the two lone pairs go opposite each other, and the remaining atoms are a perfect square, all in the same plane. So square from that direction. If we put it on the side, you can see that they're all perfectly flat. All right, so this is the other one of our flat geometries we have. Most of the geometries are not flat, but this is one of them. So another way we could draw this that's perhaps simpler is just to draw 4 90-degree angles about our central atom. Now, with the understanding that there's still lone pairs, one coming out of the page from the A, one going into the page from the central atom A, but the 5 atoms just make a nice square in this case. So we call this square planar. That's sort of the standard nomenclature. I did have an old crotchety professor in grad school who would always say, why do we call it square planar? Have you ever seen a square that's not a plane? So you could call it square. He prefers to just call it square. But you'll see probably square planar when you look at answer choices and tests and things. So it is just a square or square planar. And the bond angles in this case are exactly 90 degrees. Because again, you have equal repulsion above and below the plane, so they're going to remain exactly 90. Question? So the lone pairs, so you have to think three-dimensionally now. So if this is the plane of the square, you have one lone pair shooting out of the board towards you, and another one going into the board away from you. So I can't easily draw those in this orientation, but they are there. You have to understand that they're there. Here, I'll show you in the simulator. So that's exactly this orientation here. Okay. So you have the 4 atoms around the central atom that are all in the same plane. This lone pair is coming out towards you, and then there's another lone pair you can't even see in this orientation that's going back away from you. All right, and that's where they are when you rotate them back out. Okay, so you have to be able to think a little bit three-dimensionally for some of these, and some of them are more difficult than others to visualize. All right, so that takes us to the end of all the different electron group arrangements we're going to cover. Now let's get a couple more details and then just finish off with as many examples as we can cover in the remaining time of how to do this process of predicting the shape. All right, so first let's talk about some groups that cause bond angle compression. So we said that the bond angles have an ideal value that's defined by the electron group arrangement, but then what are some of the things that cause those bond angles to be a little bit different? So as we already talked about to some extent, lone pairs do this. If you have lone pairs on the central atom, they cause compression of the other bond angles that are around that. And also, even though with double and triple bonds, we still count them as one electron group, we don't count that as a separate electron group, those do have more electrons in them, so they repel a little bit more strongly than single bonds do. So if you have double or triple bonds in your structure, they're going to have a subtle effect on bond angles as well. Again, not a very large effect, even a smaller effect than lone pairs in most cases, but double and triple bonds do this also. So as an example, if we have the molecule POCl3, the way that we would draw the Lewis structure of this that minimizes the formal charges has a double bond between phosphorus and oxygen, and then you have 3 other electron groups. So this is going to be a tetrahedral molecule, 4 electron groups around the central atom, but because we have one double bond here, we have a little bit of a stronger repulsion between this double bond and the adjacent single bonds. So because of that, this is pushing these down, so this angle would be greater than 109.5. So if you have double bonds or other groups, if a double bond causing a compression, one of the angles is going to get larger, and then the angles on the other side are going to get smaller. So in other words, you're sort of folding the molecule over, you're forcing those positions down a little bit so that these 3 are now closer to each other and farther away from the oxygen, the group that's causing that repulsion. So again, it's a very subtle effect, though, for double bonds and triple bonds, not something that we typically talk about a lot. The other thing to keep in mind is that if you have more than one lone pair, that type of repulsion between 2 different lone pairs is the strongest. And that dictated then when we drew all these different structures that have lone pairs in them, if you have more than one lone pair, your first priority is to get those 2 lone pairs as far away from each other as possible, and then you fill in the rest of the positions. So we saw that in the AX3E2 and the AX2E3, all the lone pairs go on the triangle portion of the molecule to stay far away. And the very last one we did, AX4E2, the 2 lone pairs went on opposite sides to be as far away from each other. So that type of repulsion between 2 lone pairs is the strongest, and that's going to be the one that's most important to think about when you're deciding where to put those. All right, so that's just a little bit more about bond angle compression. What we're going to close with now is just determining a bunch of these geometries. And this is actually good for us because it allows us to also review Lewis structures. Because we cannot do this without a good Lewis structure. So you're going to have to do Lewis structures on this test. So we'll review that part of it. And then we'll take it one step further and we'll see how, once we draw the Lewis structure, we can predict then what the molecular geometry is. Okay? All right, so let's start with PCl3. We actually did the Lewis structure of that last time. So I'm not going to go through all the steps, but I'll go through the steps of some of the other ones. So if you recall, when we drew the Lewis structure of phosphorus trichloride, PCl3, what we ended up with was 3 single bonds to the chlorines. Each of these has 3 lone pairs on it, and then we also had 1 lone pair left in the central atom. So if you forgot how we did that, go back to the last notes. We'll practice a couple others today so you can see it again, how the whole process works. But we have PCl3 looks like this. And then if we want to categorize this in the AXE notation, our central atom is phosphorus. How many X's is that? How many atoms are bonded to the phosphorus? 3, so it's going to be AX3. And then how many lone pair electrons, or how many pairs of electrons are non-bonding on the central atom? How many lone pairs does it have? So it's going to be AX3E or AX3E1. All right? Now it's a total of 4 electron groups, so that's going to be falling into the tetrahedral electron group arrangement. Here we just ask for the molecular shape, but if we ask for electron group arrangement, it would be tetrahedral. It has 4 electron groups. But then the molecular shape would be, we start with the tetrahedral electron group arrangement. We place a lone pair in one of those positions. We don't really care with the lone pairs in the outer atoms, by the way. They're there, but they don't influence the geometry at all. And this gives us then what we call trigonal pyramidal. All right, so starting with a Lewis structure that we've already done, that's how we then translate that into the molecular shape or the electron group arrangement. You have to know how many total electron groups there are to get the electron group arrangement, and then the combination of X and E dictates what the molecular shape is, which in this case is trigonal pyramidal. Yes? So the wedges tells you that they're not all in the same plane. So the wedge tells you that it's coming out of the page, and the dash wedge tells you that it's going into the page, again indicating that's 3-dimensional. So again, a trigonal pyramidal is kind of like a 3-legged stool. It has the central atom at the top and then the 3 legs coming down, but they're at angles from each other, and they're not all flat. Okay? If you put the 3 legs in the same plane, they wouldn't stand up very well. Okay, so that's how we do molecular shape and electron group arrangement for that one, and we're just going to keep doing this until we run out of time. Let's do one more PCl5. So it's another compound of phosphorus and chlorine, related by the law of multiple proportions, as you'll recall, 2 compounds with the same elements. But how do they differ in shape? All right, so PCl5. Now, one thing that people are tempted to do in these problems is they look at the formula and they're like, oh, it's 5. It must be trigonal bipyramidal. But remember, we have to also count for lone pairs on the central atom. So don't skip the step of drawing the Lewis structure, because you have to know whether or not there are lone pairs on the central atom to correctly predict the total number of electron groups and the molecular shape. All right, so if we do PCl5, let's start from the beginning drawing this structure. We count electrons, phosphorus and chlorine. Going back to the periodic table, we see that it's not maximized. All right, so phosphorus is here in group 5, so it's going to contribute 5 valence electrons. Chlorine is in group 7, so they each contribute 7 valence electrons. So to draw the Lewis structure, we start by counting electrons. I might close this because sometimes it bogs down my tablet if it's running, so I don't think we'll come back to that. Anyway, so PCl5, we have 1 phosphorus that contributes 5 valence electrons. We have 5 chlorines that each contribute 7. And that gives us a total of 40 valence electrons. So in drawing the Lewis structure of this molecule, we have 40 total valence electrons, and especially for the point of doing molecular shape, we have to figure out what's the distribution of those on the central atom. All right, so we start, as always, with single bonds to all the atoms in any random arrangement to start with, as we're just doing the Lewis structure. Second step is to complete the octets of the outer atoms. Remember, with very few exceptions, all of our outer atoms are going to have complete octets, so we add in lone pair electrons to give those a total of 8, 2 from the bond, and then 6 as lone pairs. And that's what we get. Now we've used up 5 octets. We've done 5 chlorine atoms, each with an octet. So how many electrons have we used? All right, so that's all of them, right? So in this case, we don't have any lone pairs left for the central atom. We've used all 40 electrons to fill up the octets of our chlorines. So we stop here. That's our final Lewis structure. Now, as we talk about with Lewis structures, you also have to evaluate things like formal charges sometimes and all that stuff. It turns out for Vsepr, you don't really need to do that, because for Vsepr, we don't really care whether these are single or double bonds or triple bonds. You just need to know how many of them there are. So as long as you know how many things are bonded to the central atom and how many lone pairs there are, even if you don't have the Lewis structure 100% correct, you're going to be able to get the shape. Now, it turns out in this case, we are done here. These all have 0 formal charges. They all have complete octets, so we don't draw any double bonds in this case. But even in situations where double bonds are warranted, if you forget to do that, it's not going to give you the wrong shape, because it's still going to have the same number of electron groups bonded to the central atom. All right, so we stop here for this one, and then if we want to get the AXE notation, how many atoms are bonded to the central atom? 5. That can come from the formula, PCl5. We know there's going to be 5 atoms, but then how many lone pairs are on the central atom? Remember, it's only the central atom they care about, so it's going to be 0, so we could just call it AX5 or AX5E0 if you wish. So remember, 5 electron groups is trigonal bipyramidal. So the electron group arrangement is going to be trigonal bipyramidal. And the molecular shape would also be trigonal bipyramidal, because all 5 electron groups are bonded atoms, so we occupy all 5 of those positions with atoms, and then the molecular shape is going to also be trigonal bipyramidal. So again, if you don't have any lone pairs on your central atom, the electron group arrangement and the molecular shape are the same. Okay, questions on that one, on that process? Any step? All right, we can probably do at least a couple more to close out. All right, let's do IF3. So a rare compound that involves just halogens in different ratios, but these do exist. IF3. So again, we have to start by counting electrons. We have iodine and fluorine. As you're likely already familiar, because we've seen these a million times, iodine and fluorine are both in the halogen group. They're both group 7, so they both contribute 7 valence electrons for each atom of those that's present. All right, so different subshells, but still 7 total valence electrons that are involved in bonding. So with IF3, we have 1 iodine that contributes 7. We have 3 fluorines that each contribute 7. And so we have a total of 28 electrons to arrange into this molecule. All right, so with IF3 then, we put the iodine at the center. We randomly arrange the fluorines for now. We don't know what shape they're going to be in at this point. So we start with single bonds to each of those. Fluorine should get a complete octet, so we add lone pairs to complete the octet of each fluorine. All right, how many electrons have we used at this point? 24. We've used 3 octets. So we have 4 left, and remember, all the extra electrons end up on the central atom. So our iodine is also going to have 2 lone pairs. That'll complete the Lewis structure. If we evaluated formal charges for this one, they would all be 0 again. So we don't have to put any double bonds, but for Vsepr, it doesn't matter whether they're single or double bonded. A pattern you'll see is that fluorine will never form a double bond. It's not, I guess, quite as egregious as drawing more than 1 bond to hydrogen, but if you draw a double bond to fluorine, then that's also something that makes me upset. All right, so fluorine is going to just be a single bond, and that's the final structure we get. AXE notation, we have 3 atoms bonded to the central atom, 3 fluorines, and now we have 2 lone pairs, so it's going to be AX3E2. This is another case where we have 5 electron groups, so we arrange them into a trigonal bipyramidal. That's the electron group arrangement. And then if we want to draw the molecular shape, again, one way to do this is to memorize all these shapes, but I prefer to just draw it out, and it helps me at least visualize it and not make it so hard to remember. So if we do AX3E2, we have 5 electron groups. We do have to remember that that is going to involve a trigonal bipyramidal arrangement. So I at the center, in a triangle, and then one above and one below the triangle. And then we have lone pairs. Those are going to go onto the triangle, and then the fluorines go in the other position. So if we draw it this way, we can clearly see that that is going to be a T shape. All right? And just like everything we do in this class, the more you practice it, the more familiar you get with it, and you won't have to, search through the memory bank so intensely to figure these out. All right, let's do one last one. Any questions on this one? All right, one last one to close us out for the day. Let's do carbonate, CO3 2 minus. I guess we'll have a couple more to work through next time to start, but that's okay. All right, CO3 2 minus, carbonate. We have carbon, we have oxygen, and we have a 2 minus charge to account for our electrons. So carbon is group 4 valence electrons. Oxygen is group 6. Each contributes 6 valence electrons. Remember, for main group elements, the group number tells you the number of valence electrons directly. And then the 2 minus charges. So we have 1 carbon with 4 valence electrons. We have 3 oxygens with 6 each. Then we have the 2 minus charge, which adds 2 more electrons. So 22 plus 2 is 24. All right. And then if we do the Lewis structure of this, we start with single bonds to the outer oxygen atoms. We complete the octet of each oxygen. All right, and that gives us 3 octets. That's all 24 of our electrons, right? Each oxygen has 8 electrons around it now, 2 from the bond, 6 lone pairs. That's all 24. If we were doing the Lewis structure for carbonate and we wanted to do it accurately, we should recognize that right now, just like we saw in nitrate at the beginning, that the first one we did, this does not have a complete octet. So this is going to need 1 more bond. We can't just add more electrons because we've used all 24. So we should have 1 double bond in any of those 3 positions. There would be 2 resonance structures where this double bond moves around. This has formal charge on oxygen, but we can't avoid that because it's an anion. So this would be the final structure we will draw, plus 2 resonance structures. So again, if that's not clear to you, review that part because that will come up on the first test. But again, regardless of whether we do that or not, we can still predict the geometry correctly. So if we have this structure, regardless of whether we left this as a double bond, which it should be, or just left it as a single bond because we forgot that step, what's our electron group arrangement? We have how many atoms bonded to the central atom? 3, and how many lone pairs? 0. So it's AX3 or AX3E0. Again, if we left that as a single bond, we would still call it AX3. It doesn't change that. And so we get AX3 either way, and that allows us to then predict. So the electron group arrangement for 3 things is going to be trigonal planar, triangle. And because it's AX3, it's going to be, all 3 of those are going to be bonded atoms. And it's going to be, the shape also would be trigonal planar. And because of resonance, all 3 of these bonds are equal, so it still is a perfect triangle. As we said, the bonds would be somewhere in between single and double, and you can't really draw that easily, but with dotted lines to show that. So you have this delocalized double bond, 3 equivalent bonds, still trigonal planar. All right, we'll do a couple other examples next time. We'll start talking about things that you can predict once you know the 3-dimensional shape that we've talked about today.